Uniform circular motion due to a magnetic field. Since the magnetic force is always perpendicular to the charge's velocity, we're going to end up with a center-seeking force, a centripetal force, which results in centripetal motion. The charge will move in a circle. So here, for example, if we have an electron injected into this field with a velocity v, it's going to have, like at this moment here, it's an electron, so if you use the right-hand rule, or you can use the left hand, you'll see that the force will be to the right. However, that force will cause an acceleration to the right. It's going to cause a centripetal acceleration. Once the electron is here, its velocity is going this way, and its force will now be that way. When it's up here, its velocity, instantaneous velocity, will now be pointing towards the right. Therefore, the force will be down towards the center of this circle if you use the left-hand rule. So you see, you get a centripetal force. And reminder that if this was a positive charge, like a proton, then it would be moving the other direction. Circular motion was covered in AP Physics 1. Looking at the diagram on the right, can you see the relationship to the gravitational force? This could be the picture of a planet moving around the sun. What happens to the speed of a planet as it orbits? Predict what happens to the speed of the charged particle in a magnetic field. For a planet in a gravitational field, the force is always perpendicular to the displacement. So the instantaneous displacement here is this way. So this is, where it's going in that instant. And at that same instant, the gravitational force towards the sun is this way. So they're 90 degrees. Remember, the equation for work is force times displacement parallel, which becomes cosine theta. So if you have force this way and displacement that way, you have cosine 90, which is 0. So 0 work is done. Therefore, if your orbit is perfectly circular, which as we know, orbits are not perfectly circular, but if they were, no work would be done, and therefore there'd be no change in energy for the object. Therefore, the speed is going to stay constant. The same is true for a charged particle moving in a magnetic field. In both cases, the velocity is changing constantly, since the direction is changing. But the speed is constant. The magnitude of the velocity is constant. See how the length of this vector, the blue vector, is staying the same all the way around. A magnetic force cannot change the speed of a moving charge. It can only change its direction. A proton has a speed of 10 meters per second. It enters a uniform 0.25 Tesla magnetic field directed out of the page. It begins moving in uniform circular motion. Gravitational effects are negligible. What is the radius of its circular orbit? All right, so a proton has a charge of 1.6 times 10 to the negative 19th coulombs because it has the same charge as an electron, but it's positive. And a proton has a mass of 1.67 times 10 to the negative 27th kilograms. Both of these values are listed as constants on the AP2 equation sheet. Since the proton is moving in uniform circular motion, its acceleration is centripetal. So A will be equal to v squared over r. The only force acting on the proton is the magnetic field. So we're back to Newton's second law, F equals ma. So the net force equals ma. The only force is qvb. And once again, the velocity and the field are perpendicular to each other, so we don't need to worry about sine theta in here. We have mass, and then acceleration is v squared over r. Since it's not speeding up or slowing down, it's just moving in a circle, which means it has centripetal acceleration. Therefore, we can rearrange this algebraically to solve for r. And you can see that 1v here cancels out with 1v on that side, right, if you divide both sides by v. Rearrange, solve for r, and you get this. So then, I'll delete that since it was messy. All right. Oh, still not great. There we go. All right, then you plug in all your values. and you get your radius, 4.2 times 10 to the negative 7th meters. So remember, sometimes in a problem, it might seem like you don't have enough givens, but those givens might be on the equation sheet in the term in fundamental constants. So always check the equation sheet. The physics aviary has a simulation that randomly presents a charge with a certain amount of coulombs traveling in uniform circular motion in a uniform magnetic field. And they give you the strength of the field. They even tell you the radius of the orbit and the speed that it's moving at. And it asks the student to calculate the mass and kinetic energy of the particle. Click here to access the simulation. Here's an example. So given these givens, which have been rewritten here, find mass and kinetic energy. So just like before, we have F equals ma. The only force is the magnetic force, and the acceleration is centripetal. We can rearrange this equation to solve for mass. Plug in all of your givens, and we get the mass of the particle. Once we have that, we can find the kinetic energy of the particle using 1/2 mv squared. We found m, plug that in here. We were given v, put that here, square it, and we get that the kinetic energy is 4.9 times 10 to the negative 13th joules.